Thank you very much, Dr. Fonsavan. And good morning, everyone. Sabadi. I'm Jerry Shively. I'm the director of the Applied Nutrition Research Capacity Building Project. And it's my great pleasure to welcome everyone to this, our second installment in the ANRCB Nutrition Seminar Series. We're extremely fortunate to have with us today Professor Laura Murray-Kolb from the Department of Nutrition Science at Purdue University, where she serves as professor and head of the department. We're extremely fortunate to have Dr. Murray-Kolb with us because her primary work focuses on iron deficiency, especially in young mothers and their children. Dr. Murray-Kolb has been recognized for her research by the American Society for Nutrition, and she serves as a member of the editorial board of the Journal of Nutrition. Today's presentation will be recorded for later use, and you may listen in either English or in Lao. If you wish to listen to the translation in English, please find the interpretation button on your screen and select your language now. Following Dr. Murray-Kolb's presentation, we'll have a period for question and answer and discussion. And with that, I'd like to turn it over to our guest, Dr. Laura Murray-Kolb, and thank her for being with us today. The microphone is yours.
Thank you so much, Dr. Shively, and thank you for the invitation to participate in this. It's really an honor to do so today. And so I'm just very, very glad to be here with each of you. I thought I'd start by giving you just a general overview or a plan for my talk and then get into it. So at the beginning of the talk, I will start with a brief overview of the prevalence of anemia worldwide, and we'll look at some of those numbers. Then I'm going to move into how to properly assess iron status. One of the things that we're fortunate in terms of those of us who study iron is we're fortunate to have multiple biomarkers of iron status. But it can also be tricky in terms of how to interpret the measurements. And so we're going to talk a little bit about that today. And then at the very end of the talk, I will briefly review the findings with respect to iron deficiency and cognitive development. And the relationship between iron status and cognition is what my lab really focuses on. So I feel like I could give a whole talk on that. We won't have time for that today to get into a lot of those details, but I would be more than happy if people have questions, or if you want to email me afterward, or if there's an opportunity to give another talk in the future, I'd be delighted to go into more of the specifics with respect to that. But today I'm going to focus a bit more on the assessment piece of things. Okay, so I thought I would start by first just reminding all of us of some of the major nutritional concerns or problems globally. So general food insecurity is certainly a problem in much of the world. This is true in both low and middle income countries as well as high income countries. Protein energy malnutrition is certainly still one of the major concerns globally. In terms of micronutrient deficiencies, and again, this is where I'm going to focus today, vitamin A, iron, iodine, and zinc are the primary micronutrient deficiencies worldwide. We also have concerns with respect to nutrition and how it impacts reproductive health, how it impacts susceptibility to infection. And then, of course, overweight and obesity is a growing problem globally. So as far as anemia, I wanted to just take a minute and make sure that we're all on the same page, and just remind you of the magnitude of anemia worldwide. So what we see here are different categories: children less than 5 years, non-pregnant women of reproductive age, and then pregnant women. And over on the right-hand side, we see the percent or prevalence of anemia. So in children less than 5 years of age, worldwide prevalence of anemia is almost 40%. So this is a huge problem. For non-pregnant women of reproductive age, it's approximately 30%. And for pregnant women, it's about 37%. This has come down slightly in recent years, but not nearly as much as we'd like to see. So anemia is really still a very big problem globally. But I think we need to dig a little bit deeper, and we need to look at not just the overall prevalence, but where which populations are most affected. And so if we look specifically with respect to children between 6 and 59 months of age, we can see here that the burden of anemia is split pretty evenly between Africa and Southeast Asia, with a slightly higher prevalence in Africa than Southeast Asia, but again, split pretty evenly. Over on the right-hand side of the slide, you can see some of the other regions of the world. But when we look at non-pregnant women of reproductive age, we see a very disproportional distribution of the problem. And so we see that Southeast Asia, again, is really disproportionately carrying the burden of anemia in non-pregnant women of reproductive age. And this is followed by Africa as the second, as the region with the second highest prevalence. But again, you know, I think it's quite striking on this figure to see the burden in Southeast Asia with respect to non-pregnant women of reproductive age and anemia. Now, just again, so we're all on the same page, and to just remind us that anemia can be caused by several different factors. We often think of iron deficiency, and iron deficiency is one of the major causes of anemia, and that's where we're going to focus today. But I want us to remember that there are multiple other causes. Hookworm infection is certainly prevalent in many areas of the world. Vitamin A deficiency, as well as malaria infection. These are all major causes of anemia worldwide. But there are other important causes also. Vitamin B12 or folate deficiencies, riboflavin deficiency, chronic infections, especially infections such as tuberculosis, HIV, various forms of cancer, and then, of course, genetic defects in hemoglobin or the various hemoglobinopathies that we need to be cognizant of. And so I always like to either inform or remind people of the fact that anemia does not equal iron deficiency. And I think this is really important when we are trying to properly assess the iron status of a population. All too often, we use anemia as a proxy for iron deficiency. And while much of anemia is due to iron deficiency, not all of it is. And so what I'm trying to depict on this slide is, with the gray box, we see the total population represented. And then the blue box is representing those who have anemia. and the pink box is representing those who have iron deficiency. And you see that there is an overlap, of course, here of those who have iron deficiency anemia. And it's a large overlap. It's about, we estimate about half of anemia is due to iron deficiency, but it's still not equated, right? So anemia does not just equal iron deficiency. And of course, what we know is that in many regions around the world, anemia is due to multiple factors. So someone may be both iron deficient and folate deficient, or be iron deficient and have malaria. So in many places, we see anemia due to multiple factors, not just one. And so this has caused the World Health Organization to issue this statement that iron deficiency affects more people than any other condition, constituting a public health condition of epidemic proportions. So iron deficiency is a problem, and we need to make sure that we are assessing it correctly. So, like I said, I'm going to spend the bulk of my time talking about the correct assessment of iron status. So there are three compartments of iron within our bodies: the functional compartment, the transport compartment, and then the storage compartment. And over on the right-hand side of the slide, I'm depicting dietary iron absorption as well as recycling in the body. So recycling of iron occurs between transferrin, which is shown here in the middle of the figure, and the erythrocytes. And this is a lot of recycling that occurs every day, allowing us to only have to absorb 1 to 2 milligrams a day in order to maintain iron homeostasis. Okay, if we didn't have this recycling, it would be very, very difficult for us to be able to get the amount of iron into our bodies that we need in order to function. So going back to the three compartments of iron, again, functional iron. When we say functional iron, we mean iron that is carried and found in hemoglobin, in myoglobin, and in some of the various enzymes. Okay. And this is the largest compartment of iron in our body. The functional iron is the largest compartment. And we can see that again depicted in the figure over on the right-hand side. Transport iron is the smallest compartment. And this is iron bound to transferrin. And we see that right here in the middle of the figure. Again, about 3 milligrams on average of iron in our bodies is found as transport iron. And then storage iron, and here we're talking iron mostly stored as ferritin, some is stored as hemosiderin, but ferritin, with the largest storage, of course, being in the liver. And this compartment falls between, the largest and the smallest in terms of how much iron is there. Okay, so moving to iron status assessment. There are multiple factors to consider. If you are trying to assess iron status, you need to think about what is the setting. So are we talking about a clinical setting where we might have different instrumentation, or are we talking about being out in the field? We need to think about the population. Are we assessing iron in infants, young children, teenagers, adults, men, women? We need to, of course, think about our resources. what do we have available? What are the limitations? And then part of the resource, part of evaluating our resources, of course, also includes the cost, right? How much does it cost and what do we have to put toward that? So with this slide, I'm depicting the stages of iron deficiency. And not only do I want to emphasize that anemia does not equate to iron deficiency, but with this slide, what I'm trying to depict and remind everyone of is that we go through different stages as we go from being iron sufficient or having a normal iron status depicted on the left-hand part of the slide to being iron deficient anemic here on the very right-hand part of the slide. And I think it's important to remember this because, again, if all we're measuring is hemoglobin, then all we're capturing is anemia. And so even if the anemia is due to iron deficiency, we're not capturing it until this very last stage, this very severe stage of the deficiency. So just to walk you through this slide, again, here on the left-hand side, we've got someone who has a normal iron status, or this individual is iron sufficient. And you can see that their storage iron is full. Everything above this black line on the slide represents storage iron. Everything below the black line represents transport and functional iron, such as hemoglobin, the cytochromes, and transferrin. And we can see again, for someone who has normal iron status, they have plenty of iron in terms of their transport needs, their functional needs, as well as the storage of iron. But if we move from being normal in terms of iron status to being iron depleted, this stage is defined by not having enough storage iron. We can see that the transport and the functional iron are still doing okay. But if we move one more space, we see that now we have what we call iron deficient erythropoiesis. So not only have our stores been depleted, but now we're starting to see that some of the transport capacity and some of the functional iron is also being depleted. And then finally, we move to that last stage of iron deficiency anemia. And so again, just to remind you that anemia really is at the far end of the spectrum when it comes to iron deficiency. And I also want to point out here that iron deficiency without anemia has typically been found to be about 3 times as common as iron deficiency anemia. So if we're measuring hemoglobin and figuring out what the prevalence of anemia is in a particular population, we typically find that 2 to 3 times more individuals are in one of these other stages of deficiency. They haven't yet reached the stage of anemia, but they also don't have a normal iron status. And this is concerning. So how do we define the stages of iron deficiency? What do we need to be able to say someone is iron sufficient, or someone is iron deficient, or they're iron deficient anemic? So for the iron sufficient individual, we say they need to have no abnormal indicators of iron status. So you measure multiple indicators, not one single one indicates that the individual is has abnormal iron status. If that's the case, we say they're iron sufficient. As far as defining someone as iron deficient, typically we like to have 2 or more abnormal indicators of iron status. Okay, so measuring just one, might give you an indication that the individual might be iron deficient, but if you want to be very confident in the measure, we suggest 2 or more abnormal iron indicators. And to define someone as iron deficient anemic, we need to have anemia concurrent with at least 2 abnormal indicators of iron status. And then finally, for someone to be classified as anemic, they need to have an abnormally low hemoglobin or hematocrit, right? So the anemia just requires 1, either hemoglobin or hematocrit. But all of the other stages require multiple indicators of iron status in order to be confident and to properly assess and define the stage with which an individual is at. So to look a little more specifically here at some of the indicators that we have in order to define these different stages. So if we're trying to assess whether or not someone is at the iron deficient stage, this is where their storage iron has been depleted. Then the gold standard is a bone marrow biopsy. Now, we'll talk about that in a little more detail in just a minute, but that is the gold standard. But we also, thankfully, have some other measures. So ferritin is one of the measures that we have, and then total iron binding capacity is another biomarker that we have that can help us to determine whether or not someone is at the iron deficient stage. So those are the indicators that are affected early on in iron deficiency, because again, remember that the iron deficient stage is just the first stage of deficiency. If we get a little more severe in our iron deficiency, we move to the iron deficient erythropoiesis. Okay, and here we've got, again, multiple biomarkers that we can use for iron status. So transferrin saturation is one of them. Erythrocyte protoporphyrin is another. And then the third is transferrin receptor. And we're going to, again, talk about these on subsequent slides. But I do just want to point out, in terms of erythrocyte protoporphyrin, I have a little diagram that I copied here on the lower right-hand part of the slide. And here we see protoporphyrin 9 shown here. And then you can see that iron is required to convert protoporphyrin 9 to heme. Okay, so in the synthesis of hemoglobin, this is actually the last step in the synthesis. And what happens if we don't have enough circulating iron is that we get an increase in protoporphyrin, right? Because protoporphyrin now can't be converted to heme. And so we see protoporphyrin levels increase. Okay, so erythrocyte protoporphyrin is the immediate precursor of heme, and it becomes elevated in red blood cells when heme synthesis is disrupted or disturbed. And then finally, the biomarkers for assessing if someone is iron deficient anemic would include hemoglobin or hematocrit, in addition to the specific iron markers that are indicated above here. We would say at least 2 of these, in addition to hemoglobin or hematocrit. So let's talk a little bit about some of these biomarkers in more detail. So I'm starting here with a bone marrow biopsy. As I mentioned, this is the absolute gold standard. I mean, this is taking a look at, what is actually in the bone marrow. Okay, so it assesses, what we do is we take a sample of bone marrow and then we assess the stainable iron. And on the right-hand side of this slide, I've got a Prussian blue stain shown here. You can see all this pretty blue, okay, showing that there is iron in this bone marrow. But if we look on the right-hand side, we don't see any of that blue showing up, right? The stain is not showing up, and this is indicating that this individual is iron deficient, does not have discernible iron in his or her bone marrow. So it's the gold standard. It assesses for stainable iron. It has very high specificity, okay? If you see blue, you know the individual has iron. If you don't, you know the individual is depleted, okay? So the specificity is wonderful with respect to a bone marrow biopsy. However, biopsies are invasive, right? So a bone marrow biopsy in particular is quite invasive, quite expensive, and typically painful for the individual who is undergoing the biopsy. And so unless there is some other reason to do a bone marrow biopsy in an individual, even though this is highly specific and a very good way to assess iron status, it's just really not practical. And so bone marrow biopsies are not generally done if you're trying to assess an individual's iron status. So let's move to ferritin. So ferritin is another biomarker. It's a biomarker that we can detect in order to figure out if someone is at the early stages of iron deficiency. So this provides a quantitative estimate of the size of the iron stores. Does the individual have any iron stores? Now, one of the really lovely things about ferritin is that it's been validated against bone marrow biopsies. So if you take a bone marrow biopsy for every 1 milligram per liter of iron that is determined via bone marrow biopsy, that equates to 10 milligrams of storage iron. Okay, so 10 milligrams of ferritin. Ferritin is very sensitive to the early stages of iron deficiency, but once stores are depleted, it doesn't capture the degree of the deficiency. So it's important, I think, to understand this. If you are measuring ferritin either in a lab or if you send a sample out to have a ferritin measure done, and you get, the response back, you get the values back, and you see that someone has, let's say, a ferritin of 10 micrograms per liter, we would say that individual is iron deficient. However, if you also got another sample back that said this individual has a ferritin of 5 micrograms per liter, you would not be able to say that the individual with a ferritin of 5 has half as much ferritin as the individual with a ferritin of 10. And that is because of the limitation of the assay. So the assay is sensitive to deficiency, but it's not sensitive beyond that. So someone with 5 doesn't necessarily have half as much as someone with 10. All we know is that if they're on that low end, they are in fact deficient. Now, when ferritin is low, it is very sensitive. We, at least so far, have not identified a reason beyond iron deficiency that would cause ferritin levels to be low. So if ferritin is low, you can be very confident in that indicating an early stage of iron deficiency. However, the opposite is not true. So high ferritin can be caused by multiple factors, It could be caused by really high levels of iron stores, but it can also be caused by inflammation. Ferritin is what we call an acute phase protein, and acute phase proteins will change during inflammation. In the case of ferritin, it increases during inflammation. Anemia of chronic disease also causes an increase in ferritin. Thalassemia causes an increase in ferritin. So high iron or iron overload is not the only reason that you might have a high ferritin. Okay, so again, low ferritin, very sensitive to deficiency of iron. High ferritin might be high iron, but it might be caused by other things. Okay, so again, highly specific when it's low. Once ferritin is less than 12 to 15 micrograms per liter, that's typically the cutoff that we'll use. Usually we use 12 for children, 15 for men and women. It is useful for assessing iron excess as well. So a ferritin greater than 300 micrograms per liter in men or greater than 150 micrograms per liter in women generally makes us suspect iron overload. But again, you would want to rule out things like inflammation, anemia of chronic disease, thalassemia, to make sure that that high value really is reflecting iron overload. One of the really nice things about ferritin, if you're doing a study, if you're out in the field, is that it requires very little plasma or serum. So it can be done with either plasma or serum. It only requires 10 microliters. Now, typically we'll use 20 or 30 microliters because we want to run the sample in duplicate or triplicate, but it really does require a very small amount of plasma or serum. It also requires a microplate reader, so it does require some equipment. But again, thinking about different populations, oftentimes we're interested in iron status in very young infants. And it's hard to get good blood samples from very young infants. And so something that only requires 10 microliters of plasma or serum is a potentially good indicator in an infant. Okay, erythrocyte protoporphyrin. So as I already mentioned, protoporphyrin is a precursor to the hemoglobin molecule, required, of course, for hemoglobin synthesis. Erythrocyte protoporphyrin will accumulate in red blood cells when heme synthesis is impaired, okay? And we know that the assessment of erythrocyte protoporphyrin, that it has moderate sensitivity and specificity in terms of being able to identify iron deficiency. We know that it rises not only with iron deficiency, but also with things like lead toxicity, the anemia of chronic disease, and inflammation or infection. So again, that's why we say it has moderate specificity, because it's not just specific to iron, and it has moderate sensitivity because it doesn't fall at the very early stages of iron deficiency. It falls somewhere in, sorry, I said fall. It doesn't increase at the very early stages of iron deficiency. It increases somewhere in the middle stages. But it is very easily measured in the blood. It requires just 1 drop of blood, although it does require some equipment. The equipment is portable, but it requires electricity. So something to think about depending on where you're trying to do the assessment. But as you can see depicted here in the lower right-hand corner of the slide, it can be done with a finger stick. So you can do a finger stick, requires 1 drop of blood, and as long as you have the equipment and the ability to run the equipment, it can be a very easy measurement to do. It's expressed as erythrocyte protoporphyrin over heme, and the interpretation is shown here. So for children under 5 years of age, if it's greater than 61 millimoles per mole of heme, we would say that individual is likely iron deficient. For those who are over 5 years of age, if it's greater than 70, we suspect iron deficiency. Okay, transferrin receptor. So this is a receptor that is expressed on the cell surface, and it's expressed in proportion to the needs for iron within that cell. So cells acquire iron through transferrin receptor. So if a cell is deficient in iron and needs more iron, it will express more transferrin receptor. So transferrin receptor, like erythrocyte protoporphyrin, increases with iron deficiency. Okay, it has good sensitivity and specificity. It's especially helpful in distinguishing iron deficiency anemia from something like the anemia of chronic disease. And this is, it's one of the reasons is because it's not as sensitive to inflammation as ferritin is. But that doesn't mean that it doesn't change at all with inflammation. We'll talk about that in a few more slides. It is increased during increased erythropoiesis that is associated with some hemolytic conditions. So again, not just iron deficiency, but also the hemoglobinopathies, things like polycythemia vera, myelofibrosis, and some of the leukemias, as well as malaria. We are in need of more reference data for transferrin receptor. Transferrin receptor the measurement of transferrin receptor has been around for a while, but not as long as some of the other biomarkers. And so we're in need of more reference data to help establish a standard among labs. We don't currently have that. But just like ferritin, it only requires 10 microliters of plasma or serum and a microplate reader. So again, it doesn't require large volumes of blood be taken. For hemoglobin, we know that a low hemoglobin is actually how we define anemia. But again, the drop doesn't occur until the final stage of iron deficiency. So if we're doing surveys or we're doing studies and we decide we're going to measure hemoglobin as our marker of iron deficiency, one, we're not actually measuring iron deficiency, we're measuring anemia. And two, even if the anemia is due to iron deficiency, we're not capturing it until that very last stage. So we're missing everybody else who might be iron deficient, but not yet anemic. So hemoglobin has low sensitivity to iron status, and it has low specificity because it doesn't drop until that very last stage. It is specific to anemia, but not to iron deficiency anemia. We already talked about some of the other causes of anemia. And then the other point that I wanted to indicate is that the hemoglobin values that are found in iron deficient individuals and those that are found in a normal or an iron sufficient population exhibit a lot of overlap. So if you were to graph hemoglobin values in iron deficient individuals, you'll have a bell curve. And in iron sufficient individuals, you'll have a bell curve, and those two have a lot of overlap. So it makes it really difficult to determine a single value that truly separates individuals who are anemic from those who are not anemic. We still use particular cutoffs, but I think it's important to be aware that there is a lot of overlap. Now, hemoglobin, as you know, has been used in so many studies and in so many surveys because it's easy. So it is useful for large surveys. It requires 1 drop of blood, and the equipment is very portable. It's battery operated, so it doesn't even require electricity. And for this reason, I think hemoglobin gets measured in almost all studies that are looking at iron status. So I just wanted to mention some of the other red blood cell indices. So hematocrit, which is a fraction of packed red blood cells in a blood sample. Hematocrit can be measured if you're not able to measure hemoglobin, but it is less sensitive than hemoglobin, so hemoglobin is preferred. Red blood cell count can be done, but this requires typically some pretty sophisticated equipment. Mean cell volume can help us distinguish macrocytic anemia from microcytic anemia. So as a reminder, iron deficiency anemia is microcytic anemia. Cells that are iron deficient are going to appear smaller and appear pale compared to anemia that's due to something like B12 deficiency, where you're going to have macrocytic anemia. The cells are going to appear larger. Mean cell hemoglobin concentration can be another indicator, and mean cell hemoglobin. But these are not nearly as sensitive as some of the others that we've already discussed. So I like to provide this slide more as a reference point. And if you're if the slides are shared with you, you can refer back to this at some point. But again, what we have across the top is, I'll start here with the normal. This is an individual who has normal iron status. We've been discussing mostly everything to the right of this. So going from normal to iron depleted to iron deficient erythropoiesis to iron deficient anemia. But this particular slide also indicates that there is iron overload. And we've got various biomarkers shown down the left side here: ferritin, transferrin receptor, transferrin saturation, red blood cell protoporphyrin. That's the same as erythrocyte protoporphyrin. Erythrocyte morphology, what do the red blood cells look like? Hemoglobin and hematocrit. And again, I just wanted to give you this slide more as a reference so you can see, what do we generally use as cutoffs for these various biomarkers? Or in the case of erythrocyte morphology, what does it typically look like if we're looking under a microscope? And again, similar to hemoglobin, which doesn't fall until the very last stage of deficiency, the same is true about what the red blood cell looks like. If you look at a red blood cell, it looks pretty normal in terms of size and color until you get to the anemic stage, where it's small and it's pale. But I thought it would be important to include this slide, questioning whether or not we're using correct cutoffs, especially for ferritin. This is a study that was published at the end of last year in Lancet Hematology. And the authors measured hemoglobin, transferrin receptor, and ferritin. And then what they did was they graphed hemoglobin against ferritin and transferrin receptor against ferritin. And they looked to see where the inflection point occurred, okay? And they did this in children, and they did this in non-pregnant women of reproductive age. And what we see, so as a reminder, the World Health Organization, WHO, typically uses a cutoff of 12 micrograms per liter of ferritin when defining iron deficiency in a child, and a cutoff of 15 micrograms per liter when defining iron deficiency in non-pregnant women. And what they found when they graphed ferritin against hemoglobin or ferritin against transferrin receptor in both children and in non-pregnant women of reproductive age is that the inflection points appear to occur at a slightly different value of ferritin than what we're currently using for cutoffs. So for children, both for hemoglobin and for transferrin receptor, they found the inflection point at a ferritin around 20 micrograms per liter, suggesting that perhaps we're using a cutoff that's too low. So if we're saying a child has to have a ferritin less than 12 to be considered iron deficient, this is saying maybe it should actually be raised to 20. If that's the case, then there are actually a lot more children who are iron deficient than what we've been capturing. And when we look at the non-pregnant women of reproductive age, we see again that the inflection point, both for hemoglobin and transferrin receptor, is occurring around a ferritin of around 25. So again, our current cutoff is 15. If we raise that to 25, there will be even more women who are iron deficient than what we're currently capturing. Okay, so a couple of things to remember. No single laboratory value has yet been shown to be satisfactory as a sole criterion for determining prevalence of iron deficiency in populations. Okay, so again, we want to measure multiple biomarkers. There are a few different population models that have been proposed. One is called the ferritin model. That would require the assessment of ferritin, transferrin saturation, and erythrocyte protoporphyrin. One is the MCV, or mean corpuscular volume model, and this requires MCV, transferrin saturation, and erythrocyte protoporphyrin. And one is called the body iron model, and this requires ferritin and transferrin receptor. This is what is most often used in a lot of the field studies. However, there was also an article published in 2005 by May and colleagues, indicating that in the absence of being able to measure multiple specific iron biomarkers in addition to hemoglobin, it seemed that hemoglobin and ferritin were acceptable and useful for determining a population response to an iron intervention. So if you're doing a study and you're giving iron and you need to assess whether or not the population responded to that iron, and you have limited resources and you can't assess ferritin and transferrin receptor or ferritin and erythrocyte protoporphyrin in addition to hemoglobin, it seems that measuring hemoglobin and ferritin will suffice at the population level. But just to complicate things a little bit, because iron can get complicated when we're talking about assessment, there are lots of factors that affect the interpretation of iron status. And I've listed them here. So age, sex, race, altitude, smoking, pregnancy, infection, alcohol intake, and contraceptive use have all been shown to affect iron status. So the more you know about your population, the better off you are, because you can figure out whether or not you need to alter or adjust, I should say, the markers that you've measured based on these factors. So I'm going to take a look at a couple of them on the next few slides. So what we're showing here on the top left, we're looking at hemoglobin, and we're looking at hemoglobin on the y-axis and age on the x-axis. And we see that from birth to about 11, 12, 13 years of age, hemoglobin levels are steadily rising, and that's not different between males and females. But then with the onset of puberty and menarche, we start to see a deviation, right? Where males, the hemoglobin continues to rise and until they're about 15 or so, and then it pretty much evens off for the rest of their life, a slight decline toward the end. Whereas females, with the onset of menstruation, they start to have a lower hemoglobin level. And this, again, runs pretty parallel until after menopause, where you see a slight increase, but never catching up to the male level. And then you can see this is, true for erythrocyte protoporphyrin, transferrin saturation, total iron binding capacity, and serum iron. And so age and sex affect the interpretation of iron status. Elevation also does. Okay, so depending on height above sea level, you can see the effect on hemoglobin. Okay, so if you are doing a study and you happen to be at, let's say, about 1,000 meters above sea level, you would expect that the hemoglobin values you measure are going to be slightly higher than if you were, not at that altitude. And so this needs to be considered when you're trying to figure out what cutoff do I use, right? So if you are doing a study at 1,000 meters above sea level, your cutoff value needs to be increased by 2 grams per liter or 0.2 grams per deciliter. And you can see the rest as you get even higher and higher above sea level. Smoking also affects hemoglobin. So, hemoglobin. So, if the individual smokes 1/2 to 1 pack a day, you need to increase the cutoff by 3 grams per liter, 1 to 2 packs, 5, more than 2 packs, 7. Okay, so it's helpful to know, is this a smoker or not? And then here we're looking at the hemoglobin cutoffs for defining anemia. Again, this is more of a reference slide. Depending on the individual's age and sex, we have different cutoff points. Here I'm looking at ferritin levels on the y-axis, graphed against age on the x-axis. And children are typically born with a normal ferritin level, okay? This actually slightly increases at 1 month of age, but then between 1 and 6 months of age, children are getting most of their iron from their storage, from ferritin. And so between 1 and 6 months of age, ferritin levels drop. Okay, and then we see them sort of even out a bit, and then it depends, once they, if they're females or males, as adults, we get this differential mostly due to menstruation. The point that I want to indicate here is, again, this is ferritin on the y-axis, gestational age in weeks on the x-axis. And I just want to point out that ferritin accumulates throughout pregnancy. So if you have a child who is born premature, they are generally born with lower ferritin or lower iron stores. And this is going to impact their ability to have enough iron, especially for those first 6 months of life where they're living off of the iron stores. Again, this is a reference slide for you. This is showing the effect of different types of anemia on iron status indicators. So I have different types of anemia listed here in the first column: iron deficiency anemia, the anemia of chronic disease, megaloblastic anemia, thalassemia, and hemolytic anemia. And then the different biomarkers for iron across the top here. And again, it helps you distinguish in terms of, are we dealing with iron deficiency anemia, or are we dealing with the anemia of chronic disease, for instance? And you can see that ferritin can be really helpful when trying to figure out, is it iron deficiency or anemia of chronic disease? Because ferritin is low when you're iron deficient anemic, but it's high when you have anemia of chronic disease. Okay, so you can see, again, let's go to hemoglobin. Hemoglobin is no help at all, right, when it comes to distinguishing between types of anemia, because a low hemoglobin defines anemia. So it's going to be low for all of these. And that's true for hematocrit. Okay, so that's where we need to think about which iron status markers are actually going to help us, depending on the type of anemia we suspect. Okay, I want to mention measures of inflammation quickly, because as I mentioned previously, some of our iron biomarkers are also acute phase proteins. So whenever we're measuring iron status in an individual, we should also be measuring at least one, if not two, indicators of inflammation. Most often, we use alpha-1 acid glycoprotein, or AGP, and C-reactive protein, or CRP. And what I have on this slide is showing you how inflammation affects the different iron biomarkers. And so let's go here to ferritin at the bottom. And what we see is that ferritin is rapidly affected by inflammation. So within 8 hours of an inflammatory response in your body, ferritin is going to rise. And that rise parallels the rise that we see in C-reactive protein. And ferritin will increase anywhere from 30 to 100% or more. So ferritin is very sensitive to inflammation. If we instead go to transferrin receptor, we see that inflammation does impact it, but much more slowly. Okay, it takes about 24 hours, not the first 8 hours, but 24 hours. And we see that transferrin receptor levels fall. They'll fall by 30 to 50%, but not nearly as sensitive as ferritin. The same is true for hemoglobin and hematocrit. Slow or none in terms of the impact of inflammation. They might fall by 20 to 30%, but not nearly as much as ferritin. Okay, so when you're assessing, when you're trying to figure out how to assess or what are the assessment strategies, it's useful to know, are we doing screening or are we doing surveillance? So when the anemia prevalence is less than 5% in a population, screening of high-risk groups is actually more efficient than surveillance. But when the anemia prevalence is higher, greater than 5%, which it is in so many areas of the world, population surveillance may actually be warranted. So just as a reminder, when you're trying to assess iron status, we have a variety of indicators to choose from. Of course, we have to think about, some of the practical limitations. Assessing multiple indicators is going to be much more reliable than just assessing one. It's always useful to understand metabolism of the nutrient that you're interested in studying and the impact of the various physiological states of the individual. You want to know the context in which you're assessing the nutritional status. Is this a population that you suspect has a diet that's low in iron and high in inhibitors? Do you think this might be a population where multiple micronutrient deficiencies are present? What about worm infection? What about malaria? What about other types of illness? These are all things to think about. Okay. I know we're running low on time, so like I said at the beginning, what I want to do now is just show you a few slides on some of the functional consequences of iron deficiency. And this again is where my research really focuses. And so I'd be happy to answer more questions or perhaps do a whole other talk on that at some other time. But I did want to just do a broad overview here. So we know that iron deficiency is associated with a reduction in someone's physical endurance. It decreases our immune response, is associated with a higher risk of low birth weight and increased perinatal mortality. It alters our energy metabolism, our temperature regulation, and then has negative effects on behavior and cognitive performance. And again, that's where these last few slides will focus. Just quickly, I want to mention that iron has a heterogeneous distribution in the brain. Okay, so iron can be found in multiple areas of our brain, and it's higher in some areas than in others. The highest concentrations are in the basal ganglia and the deep cerebellar nuclei. If we dig down even a little bit deeper at the cellular level, the oligodendrocytes have high concentrations of iron, as well as the cortical and hippocampal pyramidal cells, tanocytes of the third ventricle in particular. And then what's also interesting is that there is a great overlap in regions of the brain that have high iron concentrations and those that receive dopaminergic and GABA tracts. This is just a reminder that when it comes to the neurotransmitters, iron is needed in the very first step of converting tryptophan to serotonin, as well as converting tyrosine to dopamine. And then quite a few things have been associated with serotonin or dopamine. So serotonin is implicated in things like memory processing and our cognitive abilities, our sleep, our mood. And dopamine, we typically think about motor functioning, reward or motivation, as well as some other factors. Iron has been found, especially in the animal literature. Iron in the brain has been found to affect morphology, so the structure really of our brain, myelination. Of course, myelin enables really rapid electrical transmission, metabolic activity in our brain. So an iron deficient brain is really an energy deficient brain. And then the neurotransmitters, which I just mentioned. So quickly here, I just want to review what has been found with respect to iron deficiency and cognitive development or cognition based on various ages. So there's a vast amount of literature on this topic in infancy, and we see consistent findings that if a child or an infant is iron deficient anemic, he or she has lower mental development test scores, lower motor test scores, their behavior is different. The child tends to be more clingy, more unhappy, more hesitant. And there's also alterations in neurophysiology. There are fewer studies that have looked specifically at neurophysiology, but they also seem to be consistent. Most supplementation studies, however, report persistent differences in the groups, even after iron treatment. So iron supplementation doesn't seem to reverse these effects. Now, you might then naturally ask the question or conclude that, oh, well, maybe it's not the iron then. Maybe it's something else. I would say there's enough evidence, especially from the animal literature, to say that's probably not a good conclusion. A better conclusion is probably that the iron deficiency is occurring during a critical period in development, and some of the negative consequences might be irreversible. And I think the message there is it's really important to make sure that we prevent iron deficiency in the first place. As far as those in the toddler and school age years, consistent findings again of lower scores on learning tasks, language tasks, motor tasks in children who are iron deficient anemic. In this age group, it seems that supplementation really does reverse the negative effects. Moving on to elementary age children, we see again a negative effect of iron deficiency anemia on performance when it comes to academic tests and learning tasks, and supplementation here seems to reverse these negative effects. If we go a little bit older to adolescents, they've been less studied, but we do have accumulating evidence that there is an association between the iron status and cognition. And in this group in particular, as well as older groups, we see that iron deficiency without anemia, so just that mild stage of iron deficiency, seems to alter cognition in these individuals. And there is some evidence that iron repletion is related to reversal of the negative effects. And then finally, in young adults, we see that iron deficiency does have negative consequences for cognition, even in the absence of anemia, and that if we improve iron status, we improve the cognition. So I want to end with what I think are some public health implications. I think it's important for us to remember that mild to moderate iron deficient individuals, which we suspect are about 1 in 4 globally, so 25% of the world's population, are often missed because a lot of times we just measure hemoglobin and we're not measuring some of these other markers. If abnormal iron biomarkers are related to decreases in cognitive functioning, then ignoring them has a real high potential in terms of cost of academic success, productivity, general well-being, and really, I would say even security of nations. And then, if we think about focusing especially on females entering the reproductive years, we have the potential to improve not only their cognition, but to increase the iron endowment that is going to go to the next generation. So I think we have we have a lot of possibilities in terms of intervening and improving health. And so this is just, again, something of a reference slide for you, indicating how these different biomarkers, iron biomarkers, can help you differentiate between someone who has normal iron status, someone who is iron depleted, who is iron deficient and experiencing iron deficiency erythropoiesis, and someone who has iron deficiency anemia. And with that, I will end and open it up to questions.
Great. Thank you very much for the presentation, Professor Murray-Kolb. I'd like to remind everyone that a link to the presentation is provided in the chat window, and a recording of the presentation will be made available. So we have time for some questions and some discussion. So I encourage everyone to either raise your hand in the chat window or indicate otherwise your interest in asking a question.
Excuse me.
Yes.
Sherry, I would ask everyone to open the camera. I'm going to do a screenshot, so the picture will be used for our seminar series update. So please welcome everyone. Open your screen.
Okay. Everyone, please turn on your camera. And while you're doing that, I'll remind everyone that our next webinar will be on December 7th. And our presenter will be Dr. Kate Edens from Indiana University, who will be speaking on the topic, social determinants of nutrition outcomes.
Looks like we may have a hand raised.
Dr. Somphun, if you want
สบายดี
Yep.
เจ้าชื่อสมพรเด้อเจ้าจากสถาบัน Yes. Hi Jerry. Thank you for your good presentation, and I interested in anemia of mother and child because last time before we had the research for mother and child, and we analyze, like you said before, if the normal weight or normal for BMI, but inside that they have anemia, iron deficiency, something like that. I saw the result and the test for exam was only 50. Okay. Yes. And we focus on CBC when we do like yes. We saw MCV and MCH before. I didn't know, but now I quite clear when I saw your presence. And for my question, I want to ask about if we use only CBC, we can teach like give the very fair for the patient, or we need more to order the test more for give the fair, something like that.
Mm-hmm.
Yes.
So I think you were going in and out a little bit there, but I think what I heard was that generally you order a CBC in order to assess some of these various blood cell parameters. But I think you're asking if you would need to order more than a CBC to determine to more specifically determine iron status. Is that what you're asking?
Yes, like that because in the rural area or for health center, maybe they have only CBC test. Yeah, something like that. If we saw the about hematocrit, hemoglobin, and MCV, MCH, right? And should we give the like a treatment like give the fair, something like that? We not sure.
Yeah. So again, I mean, so doing a complete blood count or a CBC is certainly better than having just, hemoglobin or hematocrit. So knowing like MCV, for instance, it is certainly helpful. I would encourage you, if you're able, I would encourage some of the more sensitive and specific markers of iron status, such as, ferritin, would really be the one. If you were to say, I can only do one, I could only do one additional, which one would it be? I would say ferritin would be the one that I would propose, because that is going to tell you if the ferritin is low, you can be very certain the child has iron deficiency. Of course, you have to be, just going back to, you have to be careful. If you do measure ferritin, you need to have some measure of inflammation. And so CRP or AGP are ideal. But if you have a CBC, you can also look sometimes at white blood cells as a potential indicator of inflammation. And so, that's something that you could be thinking about. But if you do measure, mean corpuscular volume, it certainly can help you start to suspect iron deficiency in the child. Did that answer your question?
Yes, thank you. For in the hospital, we have more suggestion like use ferritin or morphology, and sometimes we must to do bone marrow too.
Sure. Depending, yeah.
It doesn't hospital.
Yeah. If you are, if you're, out in a more rural situation, if you're able to get a sample and save it and bring it back to the hospital, that's something to think about. Or if you're not able to do that and you need to do something more on the spot, again, erythrocyte protoporphyrin can be a measure that might be helpful if you have the equipment that does require electricity. But we've been very creative, right, at times, and you can run different equipment off of a car battery, for instance, and things like that. So yeah, there might be some other possibilities. The final thing I will say here is that there's also the option of doing a spot. So you can do a finger prick, and you could do a blood drop onto filter paper, right? And the filter paper, the nice thing about that is the filter paper doesn't require refrigeration and freezing and all of that. So you can do a drop onto filter paper, and then you can take it back to a lab and analyze it. it's a little more complicated, but it's, as far as the actual collection and storage, when you're out in, let's say, a very rural area, for instance, that can be useful. Yeah.
Thank you so much.
You're welcome.
Yeah.
I did see a chat pop up. I wasn't sure though if it's a question or not.
No, but I guess I'll take advantage of the opportunity to ask a question. So given the challenges associated with assessment and the high degree of prevalence that one might expect to find in some populations, what is the strategy with respect to treating without necessarily assessing in advance? And what are the advantages and disadvantages of that approach?
That is a great question. We struggle with that because for some outcomes, such as just improving the individual's iron status, it seems that if you're in a population where there's a high prevalence or a suspected high prevalence of deficiency, giving sort of universal supplementation improves the iron status. And so you could say, okay, that's great. That seems to have worked well. But as we start to assess some of the outcomes like cognitive abilities and, myelination and what is going on in the brain, what is challenging is that it seems that if iron is given to a young child who is already iron sufficient, there could be harm. And, iron is, as I said, it's an essential nutrient, but it's also toxic. I mean, we do have to be careful, right? This is not a situation where more is better necessarily. And so as we start to find more of those findings where, higher levels might be harmful, it makes it a little more difficult to say, let's go in and do universal supplementation, So I hesitate a little bit on that.
Good, thank you. Other questions? If you want to ask your question in Lao, that's okay. You can ask your question in Lao and we'll have it translated.
You switch to English because you're not listening. Saying that my child is suffering.
There is a question in the chat about
Jerry,
yes.
Please you select the English in the select the one because translator try to translate to you.
Okay. Okay, now can I hear? Okay.
Would you like me to answer the question in the chat? Should I go ahead with that question, Jerry?
อันนี้คุณเจี๊ยบบอกว่า
Dr. Murray-Kolb, did you hear the question?
ข้าวหอมวันนี้
I did not. I see a question in the chat, but I didn't hear a translation of any question.
Can you hear
Can
me?
you select the English channel?
So if you go to the interpretation button, see if you can pick the English channel.
Okay. I just did that.
Okay.
Okay, can you hear me now? Okay, can you hear me now?
Yes.
ลองว่าใหม่
And how old is the child? 1.5 years. So yeah, there could be lots of things going on here. I would say with respect to the iron that it is possible that a couple of months of medication was not enough. That's certainly possible. It is also possible, I don't know if there might be a problem with lead toxicity where this individual lives, but high levels of lead can impair iron absorption. And so it's possible that when you give an iron supplement, the child is not absorbing enough. It's also possible that the child has an infection of some sort. And we know that infection raises the master regulator of iron in our body, and it causes us to not absorb much iron. So it's possible that we see this in studies where we give iron supplements in a population and the iron status doesn't change much. And if we do further assessment and we see that there's rampant infection in the population, we understand that the iron we were giving them is probably not being absorbed. So those are all potential reasons, but I would say, you know, all I focused on there was iron, of course, and there might be a lot of, you know, there might be something else going on, and it definitely sounds like something that a physician, you know, you would want a physician to follow up on. But be thinking about, you know, maybe there's an infection, so the iron couldn't be absorbed well. Maybe there's an issue with lead poisoning, you know, too much lead in the environment, and that might also be affecting iron. Okay. So another good question. we have not seen as much association between, I would say, iron deficiency and physical growth as some of the other nutrients. So my first suspicion would not necessarily be iron deficiency in a child who is not gaining as much as expected. There could be an overall nutrient issue, but if someone were going to say, is there a micronutrient that we should suspect? I would say the best data that's out there would point more to zinc than it would to iron. So a zinc deficiency has been shown to be related to less growth in children, more so than an iron deficiency. And it is not uncommon for us to find zinc and iron deficiency in, the same individual or in the same population, given the types of foods that are high in both of them. So my answer would be that if a child was gaining less weight than expected, I wouldn't necessarily say, oh, it's iron. Iron might be a factor, but iron is probably not necessarily related to the child's weight. Yes. Yeah. So yeah, there's not, you can use it. You can use it, across country. There's not a difference by country. It's not country specific. So it could be used in Laos.
Maybe we'll take this opportunity to thank our speaker, Dr. Laura Murray-Kolb, for joining us with sharing her knowledge on this topic. And as I indicated previously, there's a link to the presentation slides in the chat, and we'll also be sharing a link to the recording in the future. So thank you everyone for joining us. A reminder that our next seminar will be on December 7th with Dr. Kate Edens from Indiana University, speaking on the social determinants of nutrition outcomes. So thank you, Dr. Murray-Kolb. Let's give her a round of applause.
Thank you so much.
Thank you so much.
Thank you, everyone.
Thank you.
Thank you.
See you soon.
สบายดี